Hi class, we're going to continue with our coverage of the slope deflection method. And so the first thing that we're going to do is cover another example. This particular example is going to be very similar to one of your homework problems in that it's going to have some support settlement. So support B will settle by an amount of 0.3 inches and support A rotates clockwise by 0.003 radians. EI is given as 50,000 kip foot squared, and let's see, 0.3 inches is 0.025 feet. This is given. We are asked to solve for all the reactions. So the first step in the slope deflection method involves identifying the degrees of freedom, or DOFs. Now, had this beam been fixed at A without any support settlement in the form of rotation, then theta A would have been 0, as you all know. But in this case, theta A is given, and it's given as 0.003 radians, and because it is clockwise, we assign a positive value for the rotation at A. Again, our sign convention in the slope deflection method is clockwise is positive. So again, because the rotation is clockwise, we define that as a positive value. If we look at joint B, theta B is an unknown. So we're going to circle that. Let me focus on span AB. So what I'm thinking about right now is the slope deflection equation. We see that span AB is a general case span in that it can develop moments both at A and B. And so because it's a general case span, we're going to use the 2EI over L formulation, the general case formulation. And so in my mind, what I'd like to consider is looking at all the terms in that slope deflection equation and summarizing what the parameters are. So for span AB, we're also going to look at the possibility of a psi AB, or a chord rotation for AB. Now, if you remember, the chord rotation is simply the delta divided by the original length, the span length. And so we're looking specifically for a chord rotation. If support B drops, then point B ends up down here. Point A stays at A, and if you were to draw a line, I'm going to show it dashed here, a straight line, then the angle that the solid line, meaning the original chord, makes with the dashed line, the new chord, this is called psi AB for this span. So the way we numerically define psi AB is by, again, delta over L, which is 0.025 feet divided by the original length of 8 feet. Okay. Sometimes students ask me if the rotation at A has any influence on the chord rotation. And the answer is no. In the slope deflection method, the rotation at A is assigned its own unique value, theta A, which has no impact on psi AB, or the chord rotation. So there are two separate things, the rotation at a joint and the chord rotation of the span segment are independent. Okay? The only time that in beams that you're going to see chord rotations or psis is via a transverse support settlement, as we have here with the 0.3 inches being 0.025 feet. So when you evaluate this ratio, we get 0.003125 and the results are unitless. The units are foot over foot, or radians. Now let's take a look at span BC. If you haven't noticed yet, span BC is a cantilevering span, and so for cantilever spans we basically are not going to write out all of the slope deflection equations. In other words, remember we had the general case span and then we had the special case span. Well, this is a cantilever span, so it's kind of the third type of span that you might see. And so for cantilevering spans, you basically can solve terms using equilibrium. You can solve for example, for the moment BC using equilibrium. So you don't need to define another slope deflection equation for span BC. So what am I getting to? This is kind of one of those special cases, right? It's a cantilevering span, and so theta C is not 0 because that cantilever tip will rotate. It is an unknown, and also the vertical displacement at C is an unknown. It's not 0. They're unknowns. However, we're not going to include them, so do not include in our formulations. Okay, this is a cantilevering span. So those are not part of our solution. So the second step will be to write out the slope deflection equations, but if you remember, as part of this step, we need to figure out the fixed end moments, the FEMs. So now looking at span AB, we see that we have a general case span, and that it has a uniformly distributed load of 4 kips per foot. So the way we model this is as a fixed end with a uniformly distributed load of 4 kips per foot. This is span A, or joint A and joint B. The length is 8 feet. Again, we're going to assume everything to be positive clockwise. So we're going to call this FEM-AB and FEM-BA. We look up these terms, FEM-AB, using our handout. And the second class last time corrected me in terms of what page this was in your handouts. It's page 152 in the handout that was printed. Okay, page 152. So what I'm looking for is a fixed end that has a uniformly distributed load, and we find it right here. And so the values are WL squared over 12, but you can see that the moment at A here is counterclockwise, so we're going to artificially introduce a negative sign. So this will be minus WL squared over 12, which is equal to minus 4 times 8 squared over 12. This gives us minus 21.33 kip feet for FEM-AB. Similarly, FEM-BA is positive WL squared over 12, which is basically the same number except it's positive, 21.33. We don't have to consider span BC because, again, it's a cantilevering span, so we don't need to define a fixed end moment. We already know what the true final moment is at BC right here. We already know what that is. Well, we'll figure it out using statics anyway. So we're done with all the FEMs that we need in this problem. Now we can write out our slope deflection equations. We write out MAB is 2EI over L 2 theta A plus theta B minus 3 psi AB plus fixed end moment AB. Theta A is 0.003 radians. Theta B is an unknown. Psi AB is clockwise is positive 0.003125, and fixed end moment AB is negative 21.33 kip feet. So we make all those substitutions. We have 2, and then the EI we can also substitute for. That is 50,000 kip foot squared. The span length is 8 feet. 2 times 0.003 plus theta B minus 3 times 0.003125. Remember that the psi term has its own sign. That negative came from the negative in front of the 3. Okay, but in our case, the rotation at A was positive, so theta A, the chord rotation is positive due to the settlement. So the psi term was a positive number. So you throw that into the equation as a positive number right here. Okay, for psi AB. The negative was part of the original equation. So when you simplify this, you come up with 12,500 theta B minus 63.53. The units are in kip feet for the moment, MAB. We write out the slope deflection equation for MBA. If you look carefully, what we're doing is we're looking at defining a slope deflection equation here, right? And then this one, BC, we'll know what that is from statics again. So MBA is 2EI over L, 2 theta B plus theta A minus 3 psi AB plus fixed end moment BA. So this is going to give us 2 times 50,000 over the length of 8 feet, 2 theta B plus theta A, which was a positive 0.003 radians, minus the 3 psi, and then the FEMBA was positive 21.33 kip feet. Let's simplify this equation for MBA, and you get 25,000 theta B minus 58.36 kip feet. So now this brings us to MBC. MBC is the moment here. And as I indicated before a couple of times, we can solve for that directly using statics. So we're going to consider a free body diagram of span BC, where at B you are able, just to the right of the roller, you're able to develop a moment. And at C it's obviously a free end, so it's a cantilevering span. So this is the free body diagram that I'm going to use. And you would use something similar to this if you ever had a cantilevering span, where this is B and this is C, except that you would, instead of using 4 kips per foot, obviously you would use whatever loading is on that member, on that segment, on that cantilevering span. I'm going to define my moment MBC just to be consistent as a clockwise moment. This dimension here is 2 feet. So as you all know, we can calculate the resultant here as 4 times 2. This is equal to 8 kips. That's my resultant. And that acts at 1 foot from the fixed end. So solving for MBC, I get MBC is equal to negative 8 times 1, or minus 8 kip feet. Again, negative 8 clockwise. The next thing we need to do is, once we've identified all of our moments, we have 2 functions. and then we have a given value here for MBC that we can calculate. And we have MBA, MAB, MBA, and MBC. The next thing that we need to do is we need to look at joint equilibrium. And so I told you guys last time that what you need to do is look at the degree of freedom that you circle, theta B. That should remind you of some kind of moment at B. So we're going to look at moment equilibrium at B. So let's look at equilibrium at joint B. There's joint B. So this is MBA here, and this is MBC. Okay? Remember that the convention is clockwise on the member ends, so then it's counterclockwise on the joint. So this would be MBA, and then this is MBC. This is the free body diagram that we're looking at, the one that I've enclosed in a box. So taking sum of moments about joint B, setting that equal to 0, you can use whatever convention you want there. Just say MBA. When I say there, I mean here. Sum of moments about joint B. I'm assuming counterclockwise is positive for my equation, but you can assume it anything you want. Counterclockwise is obviously useful. MBA plus MBC equals 0. And just to remind you, this equation is not always going to give you equal to 0. If you had a moment applied at the joint in the problem statement, then that would show up as an external moment applied on the joint. But the external moment here is 0. There's nothing applied. So this is actually what I call the star equation, if you remember. This is our star equation. And the next step will be to replace MBA and MBC with their corresponding value or equation, slope deflection equation. So MBA is 25,000 theta B minus 58.36. That's MAB. And then MBC is a negative 8. Set that equal to 0, and then solve for your unknown theta, theta B. This gives us a positive 0.002654 radians. Positive means clockwise. So this joint B, is rotating in the clockwise direction. Okay, it's rotating in the clockwise direction. Joint B is. Or the beam over the support B is rotating in the clockwise direction. Whatever sign you get here, keep the sign, and then the next thing we're going to do is we're going to substitute that theta B into all of our slope deflection equations that we have up there. So this would be 12,500.002654, that's the theta B, minus the 63.53 kip feet. This gives me minus 30.35 kip feet. MBA is 25,000 times the theta B, which is 002654, minus 58.36. This gives me 8 kip feet. Okay, so these are the ones that I evaluated. These are assuming clockwise is positive. So show, in each one of your solutions, show clockwise positive, or show the clockwise moment acting. And then when you see the negative sign, switch the sign and switch the direction. So that's the moment reaction at A, that's MAB, and then this is MBA, and we remember that MBC was negative, as shown here, minus 8 kip feet clockwise. This is equal to 8 kip feet counterclockwise. And so what you can see is that these two moments are equal and opposite at joint B, as you would expect. So let's draw a final free body diagram. that shows the moments that we just calculated, and we're going to use this to calculate the remaining reactions. 4 kips per foot. We have MAB is shown here, 30.35 this way. And then just to show you what I was talking about, equal and opposite, these two internal moments are equal and opposite, which is okay. This only happens when there is no external moment applied at the joint, at joint B. Now, if you look carefully, you actually don't need those two internal moments to calculate the remaining reactions. It's fine to show them there, but you don't need to break up the structure into further smaller free body diagrams. You can just consider one big complete free body diagram and then solve for AY and BY. Obviously AX equals 0, sum of forces in the X. So we can solve for BY by taking sum of moments about A, setting that equal to 0. We get BY is equal to 21.21 kips upward. And then take sum of forces in the Y direction, setting that equal to 0. And you can solve for AY to be 18.79 kips upward. Okay, so that concludes this example. Just as a review, it's important that you recognize the settlements that are given. If the settlements for a beam are given as linear displacements of supports, then those would produce at least one chord rotation. If you see a support that is fixed undergo a rotational settlement, then that rotation is actually given to you. It's one of the thetas. In this case, it's theta A. Okay? And the last part that was unique to this example was that cantilevering span. What you want to do is you want to consider cantilevering span separate from the slope deflection equations. In other words, you don't want to write out slope deflection equations for cantilevering spans. You already can calculate what the moment is at the quote-unquote fixed end, or the cantilevered fixed end. Okay? You can just use statics, throw that moment into the equilibrium of the joint here, and then consider it there so that you can come up with your correct star equation. So that concludes this example. Okay, so for this next example, I actually posted it on Blackboard already. So if you log into Blackboard and go to course documents, scroll down, you'll see slope deflection example, the second one from the bottom. And you'll see that this is a 2-span beam. And when you print yours out, it should come out a little bit more legible than this. What I did is I already downloaded it onto OneNote and bolded some of the important regions. So this particular example, the key for this is that you have these 2 spans, and so if you were to take a moment to study these spans, would you think that these are special case spans or general case spans? And if so, how many are there? If you identified span AB as a special case span on account of there being a pin at A, you are correct. So span AB is a special case span, and so then that means that you would just be looking for a special case M bar BA moment. Now if you look at span BC, that also is a special case span because at joint C you have a roller. So this would be M bar BC. Now I'm not going to solve this problem in great detail here. You already have the handout in Blackboard. So the only thing that I'm going to do is I'm just going to try to highlight the most important parts of this problem. So number one is that you have 2 special case spans. The unknown degrees of freedom would basically reduce to 1. So the unknown degree of freedom is theta B. It is important to note that theta A is an unknown and theta C is also unknown, But again, because these two spans are special case spans, they will drop out of the equations. In other words, theta A is not part of the solution and theta C is not part of the solution. That doesn't mean they're zero, they're just not calculated. This particular problem has a support settlement at B of 1/4 of an inch. So support B settles downward. So let's say point B was there, it ends up down here. So if you look carefully, if you draw a line between point A and the new point B, draw a dashed line there, the angle that the original chord makes with this dashed new chord is psi AB. Similarly, if you draw a line between the new point B and the original point C, then the angle between those chords is psi BC. So again, I want you to label these chord rotations whenever they show up in your problems. So the next thing to note is that psi AB rotates in the clockwise direction, therefore it's going to be a positive number. And the value is basically 1/4 inches, which is 0.0208 feet, divided by the total span length. So psi AB is 0.0208 divided by 10 feet, which is the total span length. It's positive because it's clockwise, and that's shown here. And then psi BC is a negative value because the rotation is counterclockwise. And so that's going to be the same delta, which is 0.0208, divided by, again, the same 10 feet. So the main difference between these is the positive in front of psi AB and the negative in front of psi BC. We notice that only span AB has span loading. That is, it has a 40 kip-foot load applied within the span. So therefore, we're going to also look at the fixed end moment bar, FEM bar BA. That's the last term in this moment that I am clouding. So the FEM is basically shown like this. So I draw a figure of span AB with a 40 kip point load applied, and I show the FEMBA acting clockwise, because again the assumption is clockwise is positive. Now when you look this up in the handout, in the appendix section, because this is a special case span, you're going to be looking at the rightmost column of this table, and you're going to look for a point load that's acting at midspan of that span. And so clearly you see this figure applies, except that it's flipped. And so you can either imagine this beam being mirrored about a vertical line here that is something like this, and then you would see that the moment is actually clockwise as shown in this figure. The other way you can think about this is that if the load is pointing down, is pointing straight down, the arrow in the moment diagram is pointing in a similar direction, in other words downward, and so then these two moment arrows also point downward. So going back to our problem, this would be a clockwise moment. It's 3pL over 16, therefore it's a positive, so it stays as positive. For span BC, there is no loading, so the fixed end moment bar BC is 0. So no loading within the span means 0 fixed end moment. Beyond that, it's a matter of writing out two slope deflection equations, one for M bar BA and one for M bar BC. These equations would have the 3EI over L because they're the special case spans. So you would be looking at the equations that have the 3EI over L. and then plug in all the numbers as defined above, namely the side terms, the side term and the fixed end moments. So write one out for M bar BA and write one out for M bar BC, and then look at the equilibrium condition for M bar B for joint B, M bar BA and M bar BC, the sum of which will be equal to 0. Again, that's because there's no external moment applied at that joint. And then plug in your slope deflection equations for M bar BA and M bar BC into this star equation, and then you can solve for theta B. Once you have theta B, plug theta B, the value, back into the individual slope deflection equations to get the internal moments. From these you can calculate the remaining reactions. So I didn't go through this one in great detail, I just highlighted the most important aspects, but you are expected to download the problem from Blackboard and review it yourself. So the next topic that I'd like to discuss is the analysis of frames without side sway using the slope deflection method. These frames are also called non-sway frames. So for frames, we break up the discussion into two parts. One part is related to non-sway frames, and the other part relates to sway frames. So the analysis is broken up into these two types of frames. So in order to understand the difference, we have to understand what it means for a frame to undergo side sway. It's quite simple actually. Side sway is basically just the lateral deflection or the lateral rigid body translation of a frame at the floor level. Okay, so it's put simply, it's just the lateral deflection at the floor level. So floor level could be where the beams are acting. Okay? So how do we distinguish between a non-sway frame and a sway frame? Well, a frame will not sway if any of the following is true. Number one, if the frame is properly restrained against lateral deflection. So for example, if we took a frame like this and it was fixed at the base and it had a vertical load applied there, this would cause a lateral movement of the beam. However, if we were to put a support that prevents the lateral translation of that beam, then this case would be a case of a non-sway frame. So the beam cannot translate left to right. Here's another example. If you put a pin like that at that level, then this entire level is unable to move laterally. Similarly, this case was unable to translate laterally. Okay? So if the floor level is restrained physically by a boundary condition that prevents lateral translation, then it becomes a non-sway frame. It's a non-sway frame. Alternatively, let's say that the frame is unrestrained. such as excuse me, such as this frame right here. You see that the beam level, the frame is allowed to move left or right. For example, if I apply a horizontal force here, the entire frame will translate to the right at the beam level. So this would be a sway frame. But what would make this a non-sway frame? That's a good question. So in order to convert an unrestrained frame into a non-sway frame, one that does not move at the beam level, there are a number of things that have to be satisfied. The frame must be symmetric. And by symmetric, I mean, let me just list some bullet points here. I mean symmetric in terms of material. For example, the E, the modulus, has to be symmetric about an axis of symmetry, such as shown there. It has to be symmetric in terms of geometry. This includes things like the overall lengths, right? So the dimensions, the heights, for example, the heights of the two columns have to be the same. The moment of inertia, that has to do with the cross-sectional properties of the members. So you can't have one column with one cross-section and the other column with another cross-section. They have to have the same cross-section. So same cross-section, same material, and same overall geometry. But geometry also includes boundary conditions. This is something that students tend to forget. In CE 306 lab, you're going to be asked to perform an experiment to demonstrate that a frame that is symmetrically loaded does not undergo side sway, and that once you put the loading off to the side, that it will sway. And then so sometimes students will start off and just apply a load vertically right down the middle of the frame, and it looks very symmetric. And then they're going to start measuring some displacement, some lateral translation. They think that the sensors are not working properly. But one thing that they overlook is the boundary conditions. Boundary conditions are not symmetric, so you have to remember to make that frame have the symmetric boundary conditions for the lateral displacement at the beam level to be 0. So don't forget that. You'll see that in 306 lab. Lastly, the beam has to be loaded symmetrically. Okay? So for example, you can apply uniformly distributed load. And if you apply a horizontal load here, you better apply a horizontal load there of the same magnitude. Okay? And same heights, same EI for the columns. Now the EI for the columns can be different from the EI for the beams, for the beam. But as long as as long as everything is symmetric about this axis, the axis of symmetry, then this frame will not move. It will not translate left or right at the beam level. Now that's not to say that, for example, the column won't, undergo some lateral displacement like that. This lateral deflection here is not what we're talking about in terms of sway. What we're referring to sway is the actual translation of this frame like that. So an entire lateral movement in a rigid body sense. So this frame, as shown here, as long as it's fully symmetric, including the material, geometry, boundary conditions, symmetric loading, then this will not happen. Okay? This will not happen. It will not sway. So this is the type of frame that we are dealing with right now. It's a non-sway frame. And the good news is that a non-sway frame is just an extension of the beams. So if you understood the application of the slope deflection method for the solution of a beam, then the solution of a non-sway frame is simply an extension. You just have more segments. Now, the main difference obviously is that you have columns, so vertical segments. But beyond that, it's exactly the same approach. So let's consider one example. So this is a non-sway frame. Let's say that you're given this frame The two columns have the same height of 15 feet. Just going to label these joints. We also have to be given the E and the I. So E is 29,000 KSI for all the members. In this particular problem, just as an academic exercise, we are going to specify different moments of inertia for the different segments. They're trying to stump us to see if we can keep track of all this information. Okay, so all of that's given, and we are asked to calculate the internal moments at each joint. So I'll just say at each member end. So that's like MAB, MBA, MBC, etc., etc. So when we look at this, again, the first thing that I like to look for is special case spans. So can you locate the two special case spans in this problem? If you selected CE and CD as special case spans, then you are correct. So the general case spans are the other ones. So this is MAB, MBA, general case MBC, general case MCB, special case, clockwise direction, M bar CD, and special case M bar CE. So you can see that we're going to have, what is it, 2, 4, 5, 6 moment equations, 4 of which are represented using the general case equation, the 2EI over L, and 2 of which are represented using the special case formulation, that is the 3EI over L. Now let's pay attention to our degrees of freedom. So step number 1 is DOFs. So let's take a look at the thetas. So theta A is 0 because it's fixed. Theta B is an unknown. There is no boundary condition on that prevents it from rotating. Theta C is an unknown. Theta D is unknown, but it's at a pin end. It's a special case. So it drops out. It's not considered. Same thing for theta E. That's an unknown, but it drops out because of span CE being a special case span. So we are limited to theta B and theta C. Now let's take a look at the possibility of there being psi terms. So let's take, there's one psi, the possibility of one psi term for each span. So let's just methodically go through this. Psi AB is what? It's 0 because there is no chord rotation. The chord rotation would have shown up like this, okay, as shown there. There is no chord rotation because number one, point B does not move left or right. Okay, it does not move left or right. Alternatively, support A does not settle toward the left. If support A, point A, ended up over here, that would have created a psi term for column AB. Okay, so psi AB is 0. Now let's take a look at psi BC. Psi BC. So what you're looking at is the distance, well, not the distance, but the possibility of there being an angle like that, either clockwise or counterclockwise here. Now, can that happen? Well, yeah, it can happen if support D, for example, settled, because if support D settled, it brings point C down with it, and then point C would have ended up down here, thus creating the chord rotation psi BC. But in this particular example, we don't have any support settlement. So for all of the horizontal beam segments, that is BC and CE, you can create a psi term if there is a settlement, a vertical settlement present. For columns, you will create a psi term if there is a horizontal type of settlement, or also fabrication error, as will be discussed later. So to summarize, for this problem, psi AB equals 0. Psi CD is also equal to 0 because it's a column and there is no sway here, and there is no support settlement, lateral support settlement of points A or D. So we've discussed this for the beams. Psi BC is 0 and psi CE is 0. These are for the beam segments because there is no settlement, no vertical settlement in any of the supports. So in summary, there are two unknowns, that's theta B and theta C. The next thing that we want to do is to write out our slope deflection equations under step 2, SD equations. But you may recall that we want to calculate the FEMs first. That way you have all the last terms in each one of the slope deflection equations. Now, from the previous example, you probably remember that you only consider fixed end moments for spans that have loading within the span. So for example, span AB will have no fixed end moments, or the FEMs are 0. You're going to have FEMs for BC, CB, and CE bar, only the loaded spans. So let me write that down for you. So for span BC, this is the span that has the point load in the middle. We model that as a fixed beam with that point load in the middle. Please label the ends B, C, and then show me the FEMs. FEM BC, FEM CB. These are general cases. So when you look this up in the appendix section on the left column. The left column. That's for the general case. So the first case there applies. The value is PL over 8. It's hard to see there, but your handout should show it a lot clearer. So FEM BC is minus PL over 8 because it's counterclockwise in our handout. So that's -6 times, the length is 16, and then this gives us minus 12 kip feet. Similarly, this is positive PL over 8 because that is clockwise, and that gives us positive 12 kip feet. So we'll need those numbers later. And then for span CE, this is a special case span. We have to model this like this. Again, this is a special case span, span CE right there. So it's as if this joint were fixed. Three kips per foot. Show the FEM bar CE acting in the clockwise direction. Look this up in the table. You get negative WL squared over 8. Negative because the moment would actually have been counterclockwise. The length is 12 feet. So this gives me negative 54 kip feet for my FEM. So that's it. Those are all the FEMs. In fact, you have all of the values for all the slope deflection equations. The next thing is to just write out the slope deflection equations. Slope deflection equations. So in summary, you're going to have, what did we say? 2, 4, 6. 6 equations to write out. 4 general case and 2 special case spans. 2 special case equations. So MAB is 2EI over L, 2 theta A plus theta B minus 3 psi AB plus fixed end moment AB. Incidentally, had this problem, well actually this problem does do that, they give you different moments of inertia. But let's say that this problem was formulated a little bit differently. If they said EI, so let's say that column AB had 2EI, beam BC had EI. So if you had a 2EI here, for example, the point that I'm trying to make is that this would replace the quantity EI in the slope deflection equations. Okay? So if you have some parameter, an alpha EI, then in the slope deflection equation it would show up as 2 times alpha EI. Okay? So that's how you handle different values of EI there. In this case, you're given all the individual values of I, so you can just plug those in directly. Theta A was 0, psi AB is 0. For this span, FEM AB is 0 because span is not loaded. So this will reduce to the following: 2 times 29,000, that's the E, the I is 400, over 15 feet. Now be careful with your units here, because this is KSI and this is inches to the fourth, so the total units here for the numerator so far is kip inch squared. Okay, that gives you that. But you got inches in the numerator and feet in the denominator. So what I'm going to do is I'm just going to multiply by 1 over 144. So that I can convert the numerator to feet squared. And so those are the units associated with the 2EI over L. And then you have inside the parentheses, the only thing that's left is theta B, right? And then the FEM is 0. So let's clean this up. This gives me MAB is equal to 10741 theta B. The units are kip feet. This is equation 1. Let's write out a similar expression for MBA. So that's MAB, then we have MBA, general case, so that's 2EI over L, 2 theta B plus theta A minus 3 psi AB plus fixed end moment BA. So again, theta A is 0, psi AB is 0, and FEM BA is 0. This gives me 2 times 29,000 times 400, that's the moment of inertia, times 1 over 144 for the unit conversion, 15 feet in the denominator, and then the term inside the parentheses is 2 theta B. So this gives us 21,482 theta B kip feet. This is equation 2. This is for MBA. Now for MBC, again, this is a general case equation, 2EI over L, 2 theta B plus theta C minus 3 psi BC plus fixed end moment BC. So psi BC is 0. This gives me 2 times 29,000 I of 800, 1 over 144 for the unit conversion. We have 16 feet in the denominator. What's inside the parentheses is 2 theta B plus theta C, and then the fixed end moment is minus 12 kip feet. So simplifying this, it gives me 40278 theta B plus 20139 theta C minus 12 kip feet. This is equation 3. MBC. We have to write out a separate equation for MCB. General case again, 2EI over L, 2 theta C plus theta B minus 3 psi. There's only one psi per span, so that's span BC, plus fixed end moment CB. So psi BC is 0. This is 2 times 29,800, and then the unit conversion, 1 over 144, divide by the length. In the bracket terms we got, or in the parentheses, we have 2 theta C plus theta B, and then the FEM is positive 12 kip feet. So MCB is 40278 theta C plus 20139 theta B plus 12 kip feet. This is equation 4. So far we have the 4 general case equations. So MAB, MBA, MBC, and MCB. You can use this as your roadmap. So the next one that we can do is M bar CD and then M bar CE, the special cases. So let's do M bar CD. This is a special case. So M bar CD is 3EI over L theta C minus psi CD plus FEM bar CD. So psi CD is 0, FEM bar CD is 0. So psi CD, if you look at CD again, CD is the column. So the psi term for this column is 0 because you don't have any lateral settlement nor sway. So therefore you don't have any rotation of your cord, CD. And then FEM bar CD, the last term here, only deals with span loading. So since there's no span loading, then there is no FEM bar. So there's no span loading, FEM bar is 0. So this gives us 3 times 29,000 times 200 over 1 over 1 times 1 over 144 for the unit conversion, and you have the 15 feet. The only thing that's left in the parentheses is theta C. So this reduces to 8056 theta C. That's M bar CD. And then we have one more, which is for span CE. We have M bar CE, special case, 3EI over L, theta C minus psi CE plus FEM bar CE. So as before, CE, let's see, CE is a beam, it's a beam segment. So there is no chord rotation here because there is no settlement. Therefore, psi CE is 0. There is span loading, and we calculated FEM bar CE right here as negative 54. So what I'm going to do is I'm just going to write this out and say this is negative 54, psi CE is 0. This is 3 times 29,000. Moment of inertia is 650. Again, 1 over 144. The length is 12 feet for that segment. Theta C minus 54 kip feet. So, oh, by the way, this other equation was equation 5. I missed that. Do I have them all numbered? Yeah. So M bar CE is 32,726 theta C minus 54 kip feet. This is equation 6. So far we have 6 equations, 8 unknowns. Remember, we have 1 unknown for each equation. Well, that means 1 unknown for each moment. And then the theta B and theta C. So that means that we need 2 more equations. And how do we get these? Well, we're going to use joint equilibrium. So step 3, apply joint equilibrium. So, what are the 2 unknowns? The unknown degrees of freedom are theta B and theta C. So what that means is you're going to want to look at joints B and C right here, joint B and joint C, looks like a little T there, and you're going to want to apply moment equilibrium on these 2 joints. So the moments that are shown here on this figure are acting on the member ends. So they are acting clockwise on the member ends. That means they show up as clockwise moments on the free body diagrams of the members. They show up as counterclockwise moments on the joints. So you can just take this image and represent the moments as equal and opposite on each of the joints. So I'm going to start with joint B and then proceed to joint C. So joint B is going to have 2 moments acting counterclockwise, and then you can see here joint C is going to have 3 moments acting counterclockwise. So let's take a look at joint B. The joint looks like this. and the two moments will show up as counterclockwise. This is MBA and this is MBC. So taking sum of moments about point B, about joint B, setting them equal to 0, obviously you get MBA plus MBC equals 0. This is equation 7, and this is one of your star equations. So now let's take a look at joint C. This joint looks like this, and it has this moment, MCB. Again, it acts clockwise on the member end, counterclockwise on the joint. And then it has these other two special case moments, M bar CD and M bar CE. So you take sum of moments about joint C, set them equal to 0, you get MCB plus M bar CD plus M bar CE equals 0. This is equation 8. It's another star equation. So now what you need to do is you need to substitute all of the slope deflection equations into each one of these two star equations. Okay? So that means you have a slope deflection equation for each one of these moments. Plug them in, solve two equations, two unknowns. You're going to solve these two equations simultaneously for theta B and theta C. So let's demonstrate this. Equation 7, that's the first star equation. So for equation 7, we have 21482 theta B. This is MBA. Plus, it says MBC equals 0. So MBC is 40278 theta B plus 20139 theta C minus 12. This is MBC. Set that equal to 0. And then equation 8, it's MCB. There's actually three of them, right? CB, CD bar, and CE bar. So this is going to be 40278 theta C plus 20139 theta B plus 12. This is MCB plus M bar CD is 8056 theta C. M bar CD. And then the last term is 32726 theta C minus 54. This is M bar CE equals 0. Equals 0 because of the equilibrium equation there. So you have these two equations. You have to simplify them. So equation 7 star simplifies to this. And then equation 8 star simplifies to this. Okay? Solve these two equations simultaneously, and you're going to get that theta B is 2.758 times 10 to the minus 5. Theta C is 5.113 times 10 to the minus 4. Now the units for these are always radians. Because these two angles are positive, that means that the rotations are clockwise. The last step is to substitute these back into all of your slope deflection equations so that you can solve for all the member end moments. And you want to again substitute the thetas as they came out in your calculation with the original sign that came out. No need to switch signs. So the summary is as follows. MAB will be 0.296 kip feet. MBA will be 0.592 kip feet. MBC will be negative 0.592 kip feet. MCB will be 33.2 kip feet. And M bar CD will be 4.12 kip feet. Lastly, M bar CE is negative 37.3 kip feet. So now the easy thing to do is to just say clockwise, 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 etc., and then switch the ones that are negative 0.592 kip feet counterclockwise. This stays, and then this one is positive 37.3 kip feet counterclockwise. So in the end, you have the summary of all the member end moments, some of which are also reactions. So for example, if you take a look at the original problem, you have a fixed support at A. So actually in this case it's only MAB that would represent a reaction. The rest are all internal forces. Now you can break up the individual segments as we've done for the beams, so you can solve for any remaining reactions. So this concludes this example. The last example that I'd like to cover today is also posted on Blackboard. It is this last one that's called slope deflection fabrication error example. So this is a non-sway frame. You can see that support A prevents the beam from rigidly translating left or right. And what makes this problem unique is that there is a construction error, some kind of fabrication error. So the fabrication error consists of support C, the anchors for support C, to be offset by 1.2 inches too far to the right. And so there are a number of questions one can ask. One question is, well, how much force is required to pull the bottom of the column at joint C? How much force is required to pull it to the right so that the connection can be made if the support is offset? So for example, the anchor bolts are 1.2 inches too far to the right. In this particular problem, we're looking to see not only that, but also what other impact does this fabrication error create or have on the overall frame. And so looking at the slope deflection method specifically, the way to look at this is, again, you first try to identify any special case span. So do you see any? I see special case span BC and a general case span AB. So that means that you're going to be considering two general case equations, one for MAB, one for MBA, and one special case moment equation, which is M bar BC. How do we account for the fabrication error? Well, if you look at this figure in the middle of your screen, you can see that the initial chord is the vertical, direct vertical segment BC, but then the final chord is at an angle relative to the initial chord. So the angle that is made between those two lines, the one that's vertical and the one that's dashed, is the psi term. It's the chord rotation for BC. So it's a psi BC term. And how do you calculate that chord rotation? Well, it's basically the 1.2 inches over the 9 feet, but you have to use a consistent set of units. So 1.2 inches converts to 0.1 feet. Okay, so 0.1 feet divided by 9 feet gives me psi BC, as shown on the right. Now, why is it negative? Well, it's negative because as you go from the vertical to the angled line, you actually go in a counterclockwise direction. So counterclockwise is negative, clockwise is positive. So therefore psi BC is a negative value. Looking at all the other degrees of freedom, we see that theta A, because it's a fixed support without any settlement, theta A is 0. Theta B is an unknown. Theta C is also unknown, but it represents a pin condition for a special case span, so theta C remains out of the solution. So even though it's unknown, it stays unknown. We don't consider it. It's a special case span. So the only unknown degree of freedom is theta B. We take a look to see how many spans are loaded, and we see that there are no loads within any of the spans. So that means that all of the FEMs are 0, and that is indicated in the solution. So I'm not going to go through all the individual steps here, but basically you write out an expression for MAB, which is a general case expression, as the 2EI over L indicates. The FEM is 0. There is no psi AB because there's no settlement. There is no settlement that is vertical. There is no vertical settlement. There is no rotation of the chord AB. Okay, there is no chord rotation. So if I look at this here, we don't have this type of angle. That would result if you had either fabrication error this way or settlement that way as well, as shown here. Okay? We don't have that. The only thing we have is this. So we have equation 1 simplified, and then we have another equation for MBA, and then we have the final equation for M bar BC, which shows the psi term there, the psi term, psi BC. Okay, psi BC is on the far right over here, minus 0.0111. Then we look at joint equilibrium. Because the unknown is theta B, we look at joint B. So joint B has MBA and M bar BC in it. In other words, you look at the problem, you have two moments, MBA and M bar BC at joint B. So they would appear clockwise on the member ends or counterclockwise on the joint, as shown here. Take some of the moments, you get the star equation. I don't have a star shown on there. I can show it here. That's a star equation. But this one doesn't show up very well. Not as clear as this other one. So then you can substitute the slope deflection equations for MBA and M bar BC into this star equation, and then solve for theta B. Once you have theta B, plug that back into each one of the slope deflection equations, and you can solve for MAB, MBA, and M bar BC, the three moments. Beyond that, what you could do is you can, for example, break up column BC, a free body diagram for BC. You have the moment at the top of the column. That was M bar BC, was a 71.5. Okay. And then I can, there's a pin at the bottom, so you have CX and CY. And I can take some moments about the top. There's a shear at the top there, but I'm not showing it. Take some moments about the top of the column, and you can solve for CX, and you get 7.94 kips. So it takes almost 8,000 pounds of force to pull the column from the original vertical to the correct, or I should say to the current location of the anchor bolts. And so the 1.2 inches of offset, in order to make that dimension up, will require almost 8,000 pounds. And so I have a complete free body diagram here to calculate the remaining reactions, AY and CY. And then what I did beyond that was to break up segment AB and then solve for all the internal forces. Well, you already have the moment, MBA. But then I showed the shear, the axial forces there. I have the shear moment diagram for the beam, and on the right hand side you have the shear moment diagrams for the column. And then I combine the moment diagrams into one figure as shown here, and then I show the deflected shape using the curvatures. and I show support C in the offset location. Now this is exaggerated, obviously, it's not to scale. So you'll notice that the curvatures in the deflected shape will follow the curvatures of smiley faces and sad faces in the moment diagram. That was composite, that was put together. But if I look carefully at the moments that are created in the beam and column, I start with the moment negative 35.77, 71.5, and then in the column is 71.5 to 0. You can see that the maximum moment is 71.5 kip feet. So in order to give us a sense as to what this is doing, this fabrication error, just a fabrication error, what does it do to our column? What I did is I selected a W14 by 145. This is a steel section, and it has a section modulus, that's what this is called, of 232 cubic inches. Grade 50 means that that's the yield strength. That's the stress at which the material will become nonlinear. So if we calculate the stress that this moment 71.5 kip feet produces on our section, we calculate a stress of 3.7 KSI. And so typically you're going to design, if you're using allowable strength design, you'll design to a fraction of the yield strength. In other words, you don't want the loading to reach the yield strength of the material. And so for this cross section, you might design to about 25 or 30 KSI instead of the 50 KSI. So this 3.7 KSI is consuming anywhere from 12 to 15% of your allowable range. And so fabrication error can be problematic. All right, so it's important that you can handle that in your analysis as well. All right, so I hope that this was clear, and it'll require for you to take some time to look at the calculations in detail, but the most important part of this was to see how we accounted for this construction error and how it created a psi term for our column. And furthermore, we recognize our column BC as a special case span, so we want to take advantage of that as well. Okay, so this concludes not only this example but also the lecture. So I will see you on Thursday. Thank you.